Okay, welcome to lecture here. We're going to continue on for just a little bit here with chapter 14. We will then stop, and again, the exam will open up around lab time at 11:30. You can take it at that point. All right, grab a couple things here. So we've been talking about in this chapter acids and bases. We talked about definition of acids and bases. Again, Bronsted-Lowry definition of an acid is a proton donor. A Bronsted-Lowry definition of a base is a proton acceptor. Again, that creates those acid conjugate base pairs that we talked about, and the relationship that we see for those guys, again, is that they are only a difference of one H plus at a time. We also talked about calculating pH, POH, H plus, OH minus. And again, there's a couple different ways you could kind of do those things using those formulas. But remember that we do look at the pH scale as helping us determine whether or not a solution is acidic, basic, or neutral. Again, less than 7 going to be acidic, more than 7 going to be basic, and 7 there is going to be neutral. So we saw with strong acids and strong bases, we can really directly calculate the pH of the solution by either using the H plus or OH minus concentration. And that can be basically achieved by taking the formula of the strong acid or strong base and basically figuring out how much H plus is there or OH minus. So if it's a one-to-one relationship in terms of how the acid breaks apart into H plus, the concentration of the acid will be the concentration of the H plus, and vice versa. If the strong base breaks apart into sort of a one-to-one relationship in terms of the hydroxide, that will give you the hydroxide concentration, and then you could use the POH to get the POH and subtract 14 to get to your pH at that point. So when we have something that's strong acid or strong base, it's pretty straightforward in terms of determining the pH of the solution. Because they are strong acids and strong bases, we talked about last time, they 100% break apart into ions. So they completely ionize, and it makes it really easy to determine the H plus or OH minus concentration. And that's different, though, when we deal with something that's a weak acid, as we talked about towards the end as well last time. When we're doing weak acid problems, because they are weak electrolytes, they do not 100% break apart into ions. They do break apart into a little bit of ions, but mainly stay together since they are weak electrolytes. And what that means is you do get an equilibrium that's basically set up. And because you do get an equilibrium set up, you will have an equilibrium constant, which is referred to as the Ka, or the acid equilibrium constant, or ionization constant. And we need to actually do an ice table in those type of problems, because what we're looking for is, because it will not 100% break apart into ions, it will kind of go back and forth. We need to figure out what the equilibrium concentration of H plus is in the solution in order to calculate the pH, because when that system reaches equilibrium, the amount of free H plus that's in that solution will determine what the pH is. So that does require an ice table, just like we did in the previous chapters. It may be a simple ice table, it may require the quadratic formula. We still use our 5% rule if we want to try to make an assumption. The problems basically work the exact same way as our equilibrium problems. Really, the only difference is, instead of sort of figuring out the concentrations of everybody at equilibrium, usually we're more interested in just the H plus concentration. And once we get that H plus concentration, which a lot of times will equal X when you solve for X, when we do get that, the major difference is we actually will put it into the pH equation and get the pH of the solution. So again, that's a very common sort of calculation. Ultimately, it is really the same calculation as you've done before. You're just going to kind of incorporate the pH equation into the end of the calculation. And lastly, I think we finished up last time talking about the idea of percent ionization. And percent ionization is the idea of basically how much an acid, for example, will break apart into its ions. So percent ionization or percent dissociation. And in the case of an acid, basically what we're looking at is how much H plus came off, basically. And the nice thing about percent ionization is it's essentially the way that we actually do our check for our assumption. So we basically take the H plus concentration and we divide it by the initial concentration of the acid. We times it by 100. And again, here, if it's whatever that percentage is, will tell you the percent ionization. So we could use something like percent ionization like we did at the very last example to determine something like the equilibrium constant or the Ka value for an acid. And that's because typically when we would go through that problem and a weak acid dissociation, usually the H plus will equal the X value. And so we could kind of use our H plus concentration and the percent ionization to figure out the X, and then kind of work our way backwards and figure out our K value like we did there at the very end. Any questions on any of that stuff that we were talking about, I think, last time? Okay, so we talked about weak acids. So, of course, if there's weak acids, there are going to be obviously weak bases as well. And much like our weak acids, if we write our equilibrium expression for it, which is based off of our equation, as we talked about a number of times, you know, we talk about a couple of times in terms of should we include water in sort of our reactions or not. As I mentioned before, a lot of times it's a good idea to include the water in the base reactions, especially the weak base reactions, because a lot of times people really struggle to figure out what's going on this side. So with the water there acting as the acid, you know, this is the base, it's going to accept the H plus. And again, when it does that, that is really how we're generating the hydroxide on the product side there. And because it's an equilibrium, we would do our products over our reactants. And again, like normal, water would not be included because it's a liquid here. And that would give us NH4 plus times OH minus concentration divided by ammonia's concentration. And that is the Kb, obviously B for base. That kind of goes with our ever-growing list of K values. So we got our Ka now. Now we have our Kb. Again, goes with our Kw or Kc and our Kp values that we've already seen. Again, this class is basically brought to you by the letter K. But we see sort of the same thing here as we saw with the Ka. As the Kb value increases, the strength of the base, the weak base, also increases. And it's the same sort of logic here as what we had with our Ka. In general, these are all equilibrium constants. So products divided by reactants, which means, again, the larger the Kb value, we should have more products. More products means we have more free OH minus. More free OH minus means we have a stronger weak base. So again, that's how all those things sort of tie together here. Basically, what makes something a base, right, is the ability to produce free hydroxide, OH minus, in solution. And that's very similar to how it is for our weak acids as well. Again, the ability of something to be an acid is the ability to produce H plus on the product side. And again, the higher it is, or the more H plus you have, or more OH minus you have, the stronger either acid or base you're going to sort of have. And in terms of the weak part of it, again here, when we say it's a strong weak base, we're talking about in comparison to other weak bases. Strong bases, something like sodium hydroxide, do not have Kb values. And again, that is because it is a strong base, which means it will 100% break apart into ions. It is not reversible. So again, you will not have a Kb value for that. So this is, again, another sort of way that you want to think about. I see a Kb value for something, or I could find a Kb value for something, that automatically tells you that it is a weak base. So again, these are little things that you want to think about when you're doing these problems to help you identify, you know, oftentimes people have problems with, is this a weak base? Is it a strong base? You know, what am I dealing with? Again, you really want to look at, you know, the information that's in problems or that's given to you because it does give you a lot of information about, what you're dealing with. So those are good things to kind of keep in mind. So our KB here, again, products over reactants. And this is also, as we talked about last time as well, I think, a way that you know which K value you should use. Because pretty shortly here in this chapter, you will have some choices into, like, should I be using, the Ka value? Should I be using the Kb value? And the way that you could determine that is, again, as we've been talking about, looking at your actual equation here. So if your equation produces hydroxide and you're doing something with a weak acid or base, you definitely should be using a Kb value here in your calculation. And that's different than, say, earlier where we saw HF, which is our weak acid. When we look at the equation, we see H plus, I should be using a Ka. So again, those are two other very important things to keep in mind, and why it's really important to make sure that you write these equations correctly, because it will help you sort of go in the right direction in terms of the calculation. So very simple sort of rule. If you need to use sort of Ka or Kb, not sure which one to do, look at your equation. And again, if you see hydroxide on the product side, probably should be using a Kb. If you see H plus or H3O plus on the product side, probably should be using the Ka value. So again, like I said, a lot of times people do struggle with that aspect of it. And it all really comes back to the basic. You want to sort of make sure you get those equations written correctly so that you can apply the right sort of calculation. Kind of scribbled over on it, but since these are also weak base type problems, they're also weak electrolyte problems, which does mean if you are looking to figure out the pH of a weak base solution, you do need to do an ice table. Again, it's a weak base, so you're going to set up your ice table the exact same way. The major difference here between Ka and Kb problems are when you do solve for X, X does not equal the H plus concentration, as it says here when I scribbled over it. When you actually solve for X in these problems, it is actually the OH minus concentration. So usually what that means is before you can get to the pH, you will calculate the POH and then calculate the pH. So a couple of additional sort of steps with this one, again, because when you solve that ice table, you are getting the hydroxide concentration and not the H plus concentration. So you can't directly calculate the pH from that X value, but you can usually get the POH and then subtract 14 and get your pH. Any questions on that? Here's again some Kb values and table from your table. You may obviously have to look up some of these values if they're not provided for you in a problem or something like that. All right, so why don't you give this one a go and see what you come up with. We're looking at what is the pH of a 0.15 molar compound of C2H5NH2, and the Kb value is given to you. So it takes a few minutes, and give it a go. Should be good practice for a little bit later, right? Okay, so let's take a look, see how we're doing. So, again, remember that you want to look at the problem and think about some stuff that's given to you. So, again, right off the bat here, even if it didn't tell me this was a weak base, I would know it's a weak base because I do see a KB value. So, obviously, that indicates that this is going to be a weak base. And like I said, these are important things you want to kind of think about because they won't always tell you it's like a weak base in the actual problem. So what that means is I do want to write an equation here because it's a weak base because I know I'm going to have to do an ice table. And again, as we talked about earlier, usually with our weak bases, water is a good thing to throw in there. Again, it gives you an idea as to it's going to allow this base to accept that H plus. And what we're going to get is basically this guy with an extra H and the plus, and our water then will generate our hydroxide. And again, this is our equation that we're looking at in this particular reaction here. Any questions on that there? Okay, so we can write our KB for this, and our KB here going to be our products. Squeeze the OH in there. OH there on the end, and our C2H5 and H2. Again, this is a liquid, so we're not going to include it. Everybody else here is aqueous. Okay. So again, because it is a weak base problem, we know we should do an ice table. We have the concentration of our starting guy here. We don't have anybody else's given to us, so like normal, safe to assume there's going to be 0. We're going to do our change, which is minus x plus x, which means at equilibrium there, 0.1 minus x. Actually, that's 0.15 would be a better number to use there. Use the actual number, might work. There we go. Let's go with 0.15 there. X and x. Any questions on the ice table here? Okay, so again here, we're going to then put this into our KB expression. So that's ultimately going to give us x squared divided by 0.15 minus x. And that's going to equal our KB value that was given to us, 5.6 times 10 to the minus 4. We could assume x is equal to 0. And if you do, you get x squared divided by 0.15 equals 5.6 times 10 to the minus 4. And if we do all that there, we do get an x value of 0.00, we'll call it 920. And if we check that, which we should always check, then divide it by what we're going to subtract it from, which is the 0.15, and times it by 100, we got something like 6.1%, which means not so good here. So technically that's over our 5% rule. Not much, but technically speaking, it's over our 5% rule. So we do need to basically not do the assumption here. We do need to come back to this guy and really solve it using our quadratic formula here. So if we go back now and sort of distribute everything out, we will end up with multiplying the bottom to the other side. X squared equals 0.1234 minus 5.6 times 10 to the minus 4x. Bringing everybody to one side gives us x squared plus 5.6 times 10 to the minus 4x minus 0.000084. You could do scientific notation there. This again going to give us our A, B, and C that's going to go into our x is equal to minus b plus or minus the square root b squared minus 4ac divided by 2a. So here, putting in our numbers, minus 5.6 times 10 to the minus 4 plus or minus. If we put in all the numbers and kind of get a number there in our parentheses, our square root is something like 0.000336. Then if we take the square root of it, something like 0.0183 when you do all the numbers there, all divided by 2, which is 2 times 1. Going to give us 2x values doing the plus and also the minus. And doing that, we get an x value of 0.00890 or minus 0.00890. As we know and can see from our table, if we go back and look at it, we are obviously interested here in our hydroxide concentration, which is equal to x. So clearly the negative number here cannot be the right one, as that will give us a negative concentration. So that's not so good. That means that in this case, the hydroxide concentration, remember you're not getting the H plus here, is equal to x, which would equal 0.00890 molar. Any questions up to that point there? That means, as we talked about, since you do not have the H plus concentration, but you do have the OH minus concentration, you first need to really calculate the POH and get your number. So if we do that, the POH gonna be minus the log of the OH minus. That's gonna be minus the log of 0.00890. That's gonna give us a POH of 2.05. Again, a POH, in case you were confused, in case you wrote the equation wrong, which does happen, and people think what they have at this point is the H plus concentration. This shouldn't make sense to you because that would be like an acidic pH and you're talking about a base. So again, these are things you want to think about as you're doing your calculations. These are places where you can maybe fix something that doesn't make sense to you and realize maybe what went wrong, hopefully. So we do need to do the pH is equal to 14 minus the POH, and that would get us 14 minus 2.05 there. So 14 minus 2.05, try that again. Going to give us a pH of 11.95. And that does make sense since this is a base, and a pH of 11.95 is definitely basic. Any questions on any of those steps, where anything came from, why we did anything? Any questions? So hopefully as well, you can kind of see that it really is sort of the same steps. Again, the only difference is, as you can see here at the end, a reminder that when you get that X, not the H plus, but the OH, so got to go POH first and then into the pH. Any questions on weak bases or how to do weak bases there? Okay. So far we talked about Kas and Kbs and our two sort of expressions for that. So again, the top one is a Ka reaction or weak acid reaction with our Ka value. And the bottom one there is our weak base reaction. And we have our Kb value. And there is a relationship between these two things. So if we add these together, what we essentially are left with after you cancel out everything that is the same on opposite sides of the arrow is you're essentially left with water. And earlier in this chapter as well, we saw an equilibrium expression for water, which is Kw. So this brings up a really important relationship that you do need to use in a number of situations that we will come across in this chapter. And that is that if you take the Ka and you multiply it by the Kb value, that will give you your Kw. And that is our number that we saw earlier in this chapter, which is our, most cases, 1 times 10 to the minus 14. So when we add these together, basically we get our Ka times our Kb equals Kw, allowing us to find the Ka value if we know the Kb value, and allowing us to find the Kb value if we know the Ka value. And this is something that is really important to know, because we will use this in a part of this chapter when we talk about salts and hydrolysis, because there will be certain problems, as you'll see in this chapter, where they will actually give you in the problem the Ka value. And you may think, well, that's cool. They gave it a Ka value. I should probably use it. And the problem means you don't actually need the Ka value. You need the Kb value. So using this Kw relationship allows you to very quickly calculate the right value. And this is why, again, it's important to be able to write these equations correctly, because as you can see here, I have H plus, I need a Ka. I have OH minus, Kb. So, like I said, there is a lot of problems where they will actually give you, I don't want to say the wrong K value, but really the wrong K value in the application of the calculation you'll have to do. So again, important to recognize, should I be using Ka here? Should I be using Kb here? And if they give me one of those, I could again get the other one using this relationship. So again, a really important relationship. It's basically the same calculation. You take 1 times 10 to the minus 14, and you divide it by the K value they give you, either the Ka or the Kb value. Any questions on that there? All right, so we're going to talk then here about acid strength and how to determine, when comparing acids, what one might be a stronger acid versus another. And a lot of times when we sort of think about acids and their strengths, we sort of break the acids into sort of 2 categories. And these are ones that do not have oxygen involved. So basically H and usually a halogen, but no oxygen involved. So when we have this type of acid where we have a hydrogen, no oxygen involved, but it's an acid like HCl, HBr, HF, you may be tempted to go, I think, the strength of the acid is based on electronegativity. Electronegativity, right, if you remember, is the ability of an atom to attract electrons to itself. So electronegativity increases this way. And the idea here is, when you have a greater electronegativity difference, there's a greater separation of those electrons. And actually, in this particular case, when we deal with this type of acid, we actually do not look at electronegativity as sort of the major sort of value to look at in determining whether or not this type of acid is stronger or weaker. We actually look at what is known as bond strength, sometimes referred to as bond enthalpy, delta H. Yes. And bond enthalpy is basically the energy that's required to break a bond or make a bond, right? So when we break a bond, we have to put energy in, endothermic, right? They gain energy, they break apart. When we make a bond, it's exothermic. They have to release that energy so they could kind of slow down and come together. So when we look at this type of acid, something like HF, HCl, HBr, the overwhelming thing that you should look at is not electronegativity, but it actually is bond strength. And the reason for that is, in order for something to really be an acid, you need to break this bond. So the easier this bond breaks, the stronger the acid will be. And why is that? Because if that bond breaks easy, that means that this acid will generate a bunch of free H plus relatively easily. Alternate to that is if it is super hard to break that bond, if it's really hard to break that bond, it's going to hang on to that H, right? And it's not going to be a very good acid, because again, the definition of an acid is not just having an H, but it is somebody that has the ability to basically make H plus in solution. So releasing that H plus, if you will, free H plus. So when we look at bond strength here for HF, HCl, and HBr and HI, it's 565, 427, 363, and 295. So bond strength decreases as you go down, and that means that the acid strength increases. So as the bond energy decreases down group 7, the actual bond strength will increase because it only takes about 295 kilojoules of energy to break this HI bond, which means he will come off pretty easily as compared to HF, which takes almost twice as much energy to break that bond. He's not going to come off as much. So in terms of acid strength for our HF, HCl, HI increases as you go down. So HI is a strong acid, HF is a weak acid, and again, strength kind of increases coming this way. So HF weak, rest of these guys strong, and actually the strongest at the end here, again, because it has the lower bond energy. So bond energy is what you want to look at when you're dealing with an acid that does not have oxygen in it. Question on that there. Now, when we deal with acids that do have oxygen, those guys are sometimes referred to as oxyacids. And here's a graph from your book there. Kind of shows you the same thing. Again, increasing as you go down in terms of acid strength and over. So as you can see, kind of going down and over, increasing in terms of your acid strength, and your base strength is going the opposite direction here, increasing as you go this way and upwards as well. And that is the opposite relationship, if you remember right. So just so we're clear, if you remember something else we talked about, if you have a strong acid, right, its conjugate base is relatively weak. And if you have like a weak acid, its conjugate base is relatively strong. So it's that opposite relationship between those things, and that's what we see here. Strong acid here, weak base here, stronger base here, weaker acid here. So again, that opposite relationship as you go, around the periodic table there. Now, when we deal with acids that do have oxygen, as I mentioned before, they are sometimes referred to as oxy acids because they have oxygen. We do look at one of two things when we're dealing with basically this type of acid. And usually this type of acid will have this bond here, this OH bond. And usually it is like right here that needs to be broken to basically liberate that free H plus from coming off. And we look at one of two things here. We look at either the electronegativity or we look at the oxidation state. And it depends on the type of oxyacid as to which one you should look at. So let's take a look at, and again, these are all acids here. And you can see they all have the, OH bond is basically going to break. That's essentially what makes them an acid, right? Here's phosphoric acid, 1 hydrogen, 2 hydrogens, 3 hydrogens. Same thing over here, carbonic acid, which is H2CO3, are 2 H's that come off one at a time in that particular case. So the first sort of oxyacid that we're going to look at is the one like this. Here we have an oxyacid that has a different central atom that are from the same group and that they have the same oxidation number. So because when we look at each of these guys here, we have chlorine, we have bromine, they are from the same group, and they have the same oxidation number. So if you're not sure about oxidation numbers, a little reminder, and we'll talk about it in a later chapter as well, but oxygen is a really good place to start when you're assigning oxidation numbers. Oxygen is typically -2, unless it's peroxide, then it's -1. So if I were to assign oxidation numbers for my chlorine here, I would start at the oxygen, it's -2 in terms of its oxidation state. This oxygen is -2. This oxygen is -2. Hydrogen is +1. Adding all that together, that's -2, -2, and -2. That's -6 and +1. So -6 + 1 gives me -5. So to balance that out, the oxidation state here of chlorine would be +5 in this particular case. So the oxidation number of chlorine in this acid is +5. You would do the same thing for our other acid here, -2 for the oxygen, -2 for the oxygen, -2 for the oxygen, and +1 for the hydrogen. You end up with the same situation. Again, our bromine here is +5. So in this particular type of acid that has oxygen, we have two different central atoms, but they both have the same oxidation number. So in that particular case, if they're in the same group, the overwhelming thing we should look at then is electronegativity of the central atom. So in comparison of chlorine to bromine, chlorine is higher up on the periodic table, which means chlorine is more electronegative, right? Most electronegative is fluorine right there. So chlorine is the most electronegative between that and bromine, which means in general, our OH bond here, the electrons are heading towards the oxygen because it's more electronegative than the hydrogen. And now with this chlorine being more electronegative, the electrons are heading even more in. And what that essentially is doing is weakening this bond more and more and making that H easier to come off. And because it would be easier to come off, it would be the stronger acid of these two. Same thing's going to happen here. Our OH is, still the electrons are heading towards the oxygen. The bromine is not going to pull them in as much as the chlorine. Still going to weaken this bond, but not to the extent that our chlorine will because of its electronegativity. So when you're dealing with acids that contain oxygen, you want to look at the electronegativity of the central atom if they have the same oxidation number, and basically the one with the higher electronegativity will be the stronger acid, because ultimately what's happening is it will weaken that OH bond a lot more and make it easier for that H plus to come off. And again, the easier that H plus can come off, it's able to produce H plus and be considered a stronger acid. Any questions on that there? So that leaves us the third type of acid, which is also an oxyacid. The difference here is we have the same central atom, but we have different groups attached on the outside. So the previous one, we had different central atom, same oxidation number, but here we have the same central atom, different groups attached. So in this case, obviously our central atom, for the most part, is all these chlorines, right? These chlorines here. So when we're comparing guys that basically have the same central atom but different groups attached, we actually want to look at oxidation number. So again, if I were assigning oxidation number here, I would start with a -2 for the oxygen, a +1. When you add up the oxidation number, it needs to add up the overall charge. So since the charge here is 0, that means that we have a +1 for the chlorine in this situation. Coming to our chlorous acid, we have -2 for that oxygen, -2 for that oxygen, +1 for that hydrogen. That is a -3 overall. Again, to balance it out, the chlorine here would have +3. This one's like the one we just did, -2, -2, -2, and +1, giving us a -5 and a +5 for the chlorine in that situation. And lastly here, perchloric acid has 4 oxygens. Each has an oxidation state of -2. Our one hydrogen has a +1. So that is 8, -8, and +1 is -7. So our chlorine here would have a +7 oxidation state. So in comparing these, the strongest acid would be the one with the higher oxidation number. So our perchloric would be the highest, and our weakest would be the hypochlorous acid in terms of strength. Again, HClO4 to HClO, that is hyperchlorous acid at the end, perchloric, chloric acid, and chlorous acid there. So those two types of acids, oxygens, involve different central atom, same oxidation number, look at electronegativity. Same central atom, different groups attached, look at oxidation number. The idea is the same here. Our H plus, our OH here is weakened, or electrons heading this way. And then this guy here with that big +7 charge, going to bring those electrons in a little bit more, weakening this bond a lot more than when our electrons are heading in this direction and they only feel a +1 sort of attraction in. Not going to be as weak in that OH bond. Again, going to allow perchloric to generate more free H plus versus something like hyperchlorous acid, which will generate a little bit less in that sense. Question on that there. Okay, I think we'll stop there today because the next topic is going to need a little bit more, I think, time than we have left here. So we will lay it up here for today. So a couple of things before we wrap it up officially. A reminder that the exam will open at about 11:30. You are expected to start the exam around 11:30. If you do not start around 11:30, you will not get your full time allotted for the exam, which is like 2.5 hours. So if you start later than that, the computer will cut you off and everything. A reminder again that when it says end of availability, that is the last opportunity to submit your exam, not start it. So if you decide to start at like 2:40 and the end of availability is 2:50, it will only give you 10 minutes to take that exam and it won't be reopened for you. So everybody's expected to start at around 11:30. You don't start right on the nose at 11:30, but you shouldn't start too much after that. Otherwise, you will not get the whole time that's allotted for you, and you probably will need perhaps the whole time, yes, or a lot of that time, so you won't feel rushed or anything like that. So it will open up. You do need to use Proctorial, your webcam, as you did for quiz 1. And again, as I mentioned before, do your best that you can with the equipment that you got going. Again, if that requires you to maybe sit to the side of your computer, push it back, whatever it may be, in terms of your view, I like to see more than just the top of your head. I like to do your best to get you and your work area, your paper sort of area, into it the best you can. And make sure that you do have the Chrome, the Proctorial installed. If it asks you for a code, much like I told you previously, that means something is not correct. It should not ask you for a code. It will only ask you for a code if it doesn't recognize the Proctorial. So again, you may need to maybe restart it or something like that. But it should not ask you for a code for the quiz. There's a whole the exam. There's a whole module like the quiz, so you have the academic honesty agreement there to do. Once you do that, it will open up the exam. Remember that, make sure you are ready to start the exam when you do start it, because once you do, the clock will not stop and it will not be reopened. So make sure you're all ready to go. You do need to show your work. So the problems are clearly labeled in red for the problems that you do need to show work. That includes all the units, the setup, everything like normal. When you do enter your answers online, please follow what it says in each problem as to how to enter the answer for that particular problem. But just so we're clear on your work, you do need to make sure you show everything like units and all that kind of stuff when you do your work and you upload it. So once you're done with the exam, make sure you hit the submit button. You only submit the exam once. Do not submit it before you're completely done. Otherwise, it will submit a half-done exam. But it will ask you, are you sure you want to do that? You left like 20 some odd questions empty, right? I don't think there's 20 questions, but you left 20 questions empty. Hopefully that would be a warning to you. Probably not the greatest idea to do that. So make sure you hit the submit button once. Once you submit the exam, it will open up the assignment at the end of the module and that is where you can upload your work. You are expected to upload your work immediately after you submit that exam. So again, it doesn't have to be within the same minute, but really we're talking, like we talked about before, minutes from submitting your exam. So it should be submitted within minutes and stuff. Should not be like 10, 20, 30, 40 minutes. If you do it that much afterwards, you will not get credit for those problems. And there's a lot of problems that you do need to show work for. So make sure that you do that. So I say within, it should be within 10 minutes, I would think, is plenty of time to do that. So should not be a long time afterwards. Let me get some of those questions. Honestly, most of the exam is pretty much kind of work out the problems and that type of stuff. So more problem-based, I would think, not really multiple choice. I don't remember off the top of my head how many questions, but I think there's like 12-ish or 13, something like that. 12 or 13 questions, something like that, I think. And again, like I said, you do need to make sure you get that stuff uploaded as soon as possible, not super late. In my experience, I've given a lot of these. It should take very quickly. So it's not a thing like you submit your exam and then go figure out how to do all that stuff, all the problems. So just a reminder that the answer that you submit online has to match the work that you submit. And if they are different, you will not get credit for that. Also, you do need to answer all the questions online. If you do not submit an online answer, I will not look at your work. So you got to submit an online answer for every question, and then I'll look at your work. All right, so you got that. In addition, a reminder, it is closed book, closed notes, closed people, closed phone. You can use a calculator. You shouldn't have paper out to work out all the problems. Make sure that your work is clear, yes, and each problem is labeled correctly. Not like I have to figure out where one question ends and where the other question begins. So make sure, it's relatively neat as you're working through it. Obviously, no notes or anything on your papers that you should have out. Let me see here. That's that. Submit it. I don't think that you'll have too many questions. I wouldn't think so, but if you do, you can email me through. You can email me through Canvas, obviously, and I'll do my best to get back to you. But I think pretty much everything should be pretty self-explanatory. There is a periodic table there, so it's a picture and also a PDF file. Again, I'm not even sure you need it, but if you want, you could open the periodic table as a PDF file and kind of flip back and forth. Again, off the top of my head, I'm not even sure you actually need it, to be honest with you. But it's there because it's a chemistry class, I suppose. There's also some conversions on there as well in the first question or so. So some of the constants and that type of stuff is on there as well. And I believe everything that you need should be on there as well in that kind of conversion. So I think the first two things you'll see is kind of the periodic table. And then underneath that, it's like a question with some constants and conversions and stuff like that. So again, I think that should be everything that you need in terms of constants and that type of stuff. Also, don't forget that the textbook homework is due as well. So the upload spot for it is in our module page. So you make sure you upload that as well. Any questions on anything there? Also a reminder that obviously there's no lab today in terms of you don't have to log into the Zoom lecture or anything like that because there is none. And again, you're supposed to be taking the exam at the start of the lab at 11:30. So that's what you'll do for lab today. So we're not meeting for lab or anything like that. Other than that, if there is no questions, then go get yourself kind of prepared, set up, and all that good stuff. I was a little slow uploading the online homework for you to upload, so I think I made it due tonight at 11:59. So I'll give you some extra time if you don't have to do that, but you could upload it now if you want. But I think it says 11:59. Usually it's due right, before we take the exam, but I kind of forgot to pop it up there, so I just gave you some extra time and stuff like that. Okay, so again, a reminder, get it all set up. Have a nice weekend. We'll continue lecturing on Tuesday on this chapter, and we'll continue the experiment that we're doing on Tuesday as well. Make sure you do upload the experiment as well that you have due today. So make sure that gets uploaded too. All right, good luck on your exam. Well, one last thing, just so you know, the score that you see at the end that it may give you is probably not going to be your final score. I do go back and look and make sure, that nothing was marked wrong for the computer, the way you entered it. I do look at your work to give you partial credit and stuff like that. So if you're given a score at the end of the exam, don't freak out. It may be low, because the computer graded it. But I am going to go back and obviously adjust and make any appropriate adjustments to your score. So take it with a grain of salt if it does give you a score at the end. Again, in most cases, probably not going to be your final score, I would say in most cases. Usually it will go up, I would think, in most cases. Can't guarantee, but usually it goes up, I would think, in most cases. So again, take that with a grain of salt until it's officially graded. Other than that, good luck on your exam. Again, if you have any questions, feel free to email me. But I think it should be pretty self-explanatory. And I wrote a lot more instructions and stuff like that. So make sure you look at each question and make sure you enter it the way it tells you to do so. All right, have a nice weekend. Good luck on your exam. Again, it will open up around 11:30. It'll be in the module section, and an announcement will come out with a link just to let you know that it's open and all that good stuff. Again, remember, you need to start around 11:30. If you choose to start later than that, you get whatever time is left on the clock. All right, so have a good rest of your day and have a good weekend.